So now we are going to focus on the sampling distribution of the sample mean in different situations when we are drawing the sample from the normal population. So in this case, the first scenario is when the population variance is known to us. See, normal distribution has two parameters. One is the mean and the other one is the variance, mu and sigma square. Now, since we are finding out the sampling distribution of sample mean, it means our focus is on the population mean. Now, what is the other parameter that is left to us? That is the variance, right? Now, there can be two situations. This population variance could already be known to us or it might be unknown to us. So that is why the corresponding sampling distribution also varies in these two situations. So first we will understand what will be the sampling distribution of sample mean when the variance is known. That is the population variance in case of normal distribution. So this is the result, which basically says that if you have a random sample of size n coming from a population, then in that case, sample mean denotes the, x bar denotes the sample mean and sigma is the population standard deviation, then the sample mean follows normal distribution with mean mu and variance sigma by root n. Or equivalently, if you standardize it, you would see that it is x bar minus mu over sigma by root n follows normal distribution with mean 0 and 1. Now, in order to prove this, you know that if we have to prove the distribution, if we have to obtain the distribution of any function of the random variables, then we can use either the transformation technique, we have the distribution function technique, or your MGF technique. So in this case, since we know the MGF of the normal distribution, we can find out the MGF of the sample mean, and by looking at that, we could identify whether it is normal distribution or not. So let us see the proof of that. So our third theorem says that if you are drawing a random sample from normal population with mean mu and variance sigma square, and you calculate the sample mean, in that case it would follow normal distribution with mean mu and variance sigma square by n. Okay, so in the previous theorem, we have seen that expectation of x bar is mu and variance of x bar is sigma square by n, but from there we cannot say anything about the distribution of the sample mean. Okay, so now we have this theorem which says that if you are taking a random sample from normal population, then its sample mean again will follow normal population only, but it will have the mean as same, but the variance over here varies, that is sigma square by n. So in order to prove that, we will use the MGF result that we have just now obtained earlier also over here, right? So this is what? This is moment generating function of x bar at t, right? Since this holds true for any population, it will also hold true for the normal population also. So keeping that in mind, the proof over here says that mx bar so this is same as moment generating function of x at t by n whole to the power n. Now, what is the moment generating? Since x is what? These are xi's, right? They are identically distributed. I can just simply consider x. And what is the MGF of the normal distribution? We all know that MGF is e raised to the power mu t plus sigma square t square by 2. So here, if we substitute it, it would be e raised to the power, so instead of t, it would be t by n plus sigma square t square, or we can say we can just write t by n whole square by 2, this whole to the power n. Okay, so now this would be same as if I write e raised to the power n mu t, and this is same as writing the same thing, n mu t by n plus sigma square t by n whole square by 2 okay, so n will cancel out, you would be left with e raised to the power mu t plus you would have sigma square by n into t square by 2. So if you compare this MGF and this MGF, so here the distribution is mu sigma square. In this case, what it will be? It will be normal. Mean will be the same because mu t is there. And you can see that instead of sigma square, you have t square by 2 in both the cases. Only the sigma square is varying. So that is, you can write sigma square by n. So this is the MGF of your sample mean. So from here, you can say that X bar basically follows normal distribution with mean mu and variance sigma square by n. Okay. Now, if this holds true, then we could also say that X bar minus mu sigma by root n, this is going to follow normal, mean 0 and variance 1. How do we get this? This you can prove X is following normal distribution with mean mu and variance sigma square. Then if you define Z as X minus mu by sigma, this is going to also follow your normal with mean 0 and variance as 1. So let us consider an example over here. Suppose you consider the population of 1000 light bulbs with an average lifespan of population mean there is 30.340 months and standard deviation is approximately 32 hours. And if you consider the histogram over here, then you would see that it would look something like this. So here what you see is that it is right skewed, right? However, in this case, if you estimate the behavior of the sample mean based on samples of size 5, 10 and 30, then in that case, so when you have a skewed population and you just take a sample from that and you plot it, you will again get a skewed data only. Okay, this distribution or the histogram would be right skewed in this case. However, if you take a sample of size 5 from those 1000 bulbs, find their sample mean, mark it, then again you take some other sample, right? So you can choose basically 1000, choose 5 samples, these many number of samples that you draw each time, and then you plot the sample means, then the frequency distribution would look something like this. Next, if you take samples of size 20, then the sampling distribution would be in this way. You see that as we are increasing the sample size, the histograms over here, these histograms are becoming normal. Okay, if you see that if you take samples of size 30, every time you take a sample of size 30, note down its mean, again you take a sample and redo it again and again. So what you get over here is that your distribution starts to become normally distributed. Okay, although the original population is skewed, but when you are finding out the sampling distribution of the sample mean, in that case it is getting normally distributed. So if you summarize what are the observations from these figures, you see that when you take just the population itself, mean is 30.34 and standard deviation is this, right? When we take sample size of 5, then mean remains the same, but standard deviation over here is this, which is very much close to sigma by root n, because sigma is what? 32.762 divided by root 5. This would be approximately 14.652, and what you have obtained is this. Okay, so if you take more and more number of samples, this would become more and more evident. It will become almost same. Likewise, if you move to 20 size samples, then in that case, again you see that mean is approximately the same, whereas the standard deviation of the x bar is becoming this, which is again, if you divide this 32.762 by root 20, then you would get this. Okay, likewise for the third one. So in each case, what you observe is that although the x bar, that is expectation of x bar, if you see, mean remains the same in all, approximately same in all the three scenarios, but standard deviation is getting divided by root n every time. And that is what we saw earlier also, that if you have expectation, then expectation of x bar is mu, but variance of the sample mean becomes sigma square by n. Okay, this here also we observe the same thing. Also, note that when we are talking about the standard deviation of the sample statistic, then we refer to it as the standard error. So instead of just saying standard deviation, we refer to it as the standard error. Okay, and this brings us to the next important theorem, which is your central limit theorem. Central limit theorem basically says that if you are drawing a sample from a population and you are noting down its mean, again and again you take out samples, and when you mark their sample means and plot it, the resulting distribution would be normally distribution. No matter what the original population was, be if it is skewed, then also you would reach to normal distribution. If it is normal, then obviously you would get normal, provided your sample size approaches infinity. Okay, and equivalently this statement would hold true, as we have seen earlier also. How do we get this? Okay, so to understand this, let us consider a situation, and each of them would have an equal chance, and the probability would be 1 by 6 for each of them, right? This is the situation when you just have a single die. If you roll a die, this is what you get. Now, suppose you are given 2 die, then what you will do? You will roll both the die, and then you will note down their sample means, and then you will mark them. Again, you will roll it multiple times. You will keep on doing that, and every time you will take the mean of those two, mean of the upper faces of the 2 die. Then what will happen is that you will see that these start behaving in a different manner. Okay, so it becomes something like this. Now, if you keep on adding the number of dice, as suppose now you take 5 dice and then again you plot them, you take the sample mean, plot them and keep on doing this, and you finally, if you move to more number of die, then what you will see is that it starts to get more and more symmetric, that is more and more normally distributed. So you will see that it becomes something of this shape. Okay, so you see that it is getting symmetric over here. Then so here we see that as we increase the number of die and keep on taking the sample means, then your observations are going to follow your central limit theorem. So these are the distributions of the average scores. Okay, so these are the sample means over here that we are taking. First for 2 die, then we have taken 5 die, and then we are taking 10 die. So as we move ahead, so now we are going to see few examples based on your central limit theorem. So in this example, we are given that in an engine manufacturing company, the durability of the engines is approximately normally distributed with a mean lifespan of 600,000 kilometers and a standard deviation of 50,000 kilometers. Find the probability that a random sample of 25 engines will have an average life of more than 6,25,000 kilometers. Now, so first of all, in order to solve this, let us note down what is the information that is given to us. So we are already told that they are coming from a normal population. Mean lifespan is, so this is basically your mu. So we will note that down, 600,000 over here. And a standard deviation is 50,000, that also we will note down. And find the probability that a random sample of 25 engines, so it means the sample size over here is 25, and we have to find probability that sample mean, okay, we are talking about average life, so sample mean is greater than equal to 625,000. We have to find this probability. So I have noted this down. So mu is given to us, okay, sigma is given, n is 25, and we have to find this probability. So in order to find this, we already know that sample mean follows normal distribution with mean mu and variance sigma square by n, because we already know that it is coming from a normal population. So sample size of less than 30 is also applicable in this case. So first of all, we are going to standardize this. So what we will do, probability that sample mean x bar minus mu sigma by root n, right? This is greater than equal to, so from the right hand side also you will subtract the mean, that is 600,000, and you will divide by 50,000 divided by square root of 25, that is 5 over here. So this basically corresponds to, so this term over here, this is basically your standard normal variate that follows your normal distribution with mean 0 and variance 1. And what do you get on this right hand side after inequality? So if you solve this, basically what you get is, so this is root 25, so that will be 5, and this will cancel out, and finally you will get something around, so here let me just write it, 625,000 minus, so I can just write this, and so here root 25 is 5, so it will be 10,000. So basically this is 2.5, probability that z is greater than equal to 2.5. Okay, and if you look at the standard normal table, this basically corresponds to probability somewhere around 0.00621. Okay, you can check this from your standard normal table for this value. So in your question, they ask that what is the probability that the average lifetime is going to be greater than this, given that the population mean is this. Okay, so in this case you have found that the probability for such a thing to happen is very, very low, because it comes out as 0.006. So this is the next example over here. In a forest ecosystem, the heights of a group of trees follow a distribution with a mean of 30 feet and a standard deviation of 3 feet. So mean is given to you and standard deviation, that is mu and sigma, are given. If a sample of 36 trees is randomly chosen, estimate the probability that the sample mean of their heights fall between 27.5 and 31 feet. Okay, so note that here we are not given that what is the distribution of the population, right? However, we know that a sample of 36 trees has been taken. So by the general notion is that if it is greater than 30, you can apply the central limit theorem, even though the population is not normally distributed. So let us solve this. So what we are given, so in a second example, we are given mu as 30, sigma is 3, n is 36, and you have to find the probability that the sample mean lies between 27.5 and 31. So here we have to find probability that sample mean falls between 27.5 and 31. Okay, so we need to subtract the mean from all these three terms and divide by sigma by root n. Okay, so sigma by root n, if you see from here, what it will be? 3 by root 30. Okay, sorry, sample mean was given to us as 36. This is not 30. So this will be 36. So this is 36. So 3 by root 36, 3 by 6, which is 1 by 2. Okay, so let me solve over here. Probability, so you will subtract the mean, that is 30, and when you divide by sigma by root n, that is 1 by 2. Here also you will do the same thing, x bar minus 30 divided by 1 by 2 and 31 minus 30 divided by 1 by 2. Okay, so what you find over here is, so here you will get minus 3 on this side. Okay, this will be less than equal to z, because this is now following standard normal distribution, and this side we will have 2. Okay, now whenever we have to find the probability that x lies between a and b, so probability that a lies between a and x lies between a and b is nothing but distribution function f of b minus f of a, right? Or you can say that probability that x is less than equal to b minus probability that x is less than equal to a. Since we are dealing with continuous distributions, you can put equality also, the result would be the same. So here probability that x is less than equal to b minus probability that x is less than equal to a. So here the same thing would apply. So probability that z is less than 2 minus probability that z is less than equal to minus 3. And if you look at the standard normal table, substitute these values, so it would somewhat come around 0.97 or 98. Okay, so you can cross check these values. So the goal is to tell you the method, how it is done and how to deal with any problem. Next, in an investigation focused on predicting the delay duration, which is basically the difference between the actual arrival time and the scheduled arrival time of aircraft arrivals at an airport, based on the past data, it has been found that the smallest delay that was recorded was minus 27 minutes, while the largest delay was 123 minutes. Determine the probability distribution for the sample mean of a randomly selected set of 100 delay times. So in this, again, if you see, you have to find the probability distribution for the sample mean, and the sample size over here is 100, and it is uniformly distributed from -27 to 123. So the delay can be anywhere in between this. So if we have to solve this, so let us do it. So this was our second, I think if you go by the numbering, so this is second, this will be third example over here, and now we have the fourth example. So if you denote the arrival so basically if you denote the delay time of an aircraft, so your D is the delay time, okay, is the delay time of aircraft at an airport, then basically T is following a uniform distribution with parameters -27 and 123. So if you have to write this density, this would be somewhat, so it is 1 over A plus B, so this is basically 150, and here it would go from -27 is less than equal to T less than equal to 123, and it will be 0 otherwise. Okay, this is the delay time of aircraft which is given to you. So it means that here it is coming from a uniform distribution. There is no mention about normal distribution. So if you plot it, it would look somewhat like, so here you have -27 and here you have 123, and the equal probability is there of 1 by 1 over 150, right? So this is given to you, this is uniformly distributed. Now it says that here what will be the mean over here based upon this density. We know that mean for the normal distribution, mean for the uniform distribution with parameters A and B is basically A plus B by 2. So in this case, A is -27 and this is 123. Okay. So basically what you get is 96 by 2, and which is 48. So mean you have obtained as 48. Similarly, the variance, if you are finding out the variance for uniform distribution, it is B minus A whole square by 12. Okay. So again, if you substitute, so 123 minus of -27, that would be plus whole square by 12, which is 150 whole square. So it would be somewhat around 1875. So you can check this. Okay. Now for the sample mean, if I have to find this distribution, so these two, mu and sigma square, this is all about the population over here. We now are interested in the sample mean, and the sample is of size 1000. Okay. So the sample mean based on the central limit theorem will be following normal with mean mu and variance sigma square by n. So it means mean will be same 48, but sigma square by n. So n is 100, and if we divide it, so it means sample mean would follow normal, mean will be 48, and this will be 18.75. Okay. So now this was for the uniform. If you have to plot this, so somewhere around here, the peak will come and then it will go down. Okay, so here you will have your mean over here. So far what we have seen is, what is a sample statistic we have seen. Then we saw how to calculate the expectation and variance of the sample mean. If it is coming from any population, what will be the MGF? We have also seen that. Then we moved on to the normal population for a single sample problem. If we are interested in normal population has two parameters. Okay, our interest is in mu. Okay, and we are interested in finding the sampling distribution of this sample mean. We are left with another parameter, sigma square. So sigma square if it is known, then we found that x bar would follow normal with mean mu and variance sigma square by n. This is the first situation. The second case would be where sigma square is unknown. If sigma square is unknown and we are interested in this distribution of x bar, okay, then what change will come over here? You might think that since sigma square is unknown, sigma square is the population variance, we could estimate it, or we could replace it simply by sample variance in this formula, in this distribution over here, right? Because what is this? This is basically saying that x bar minus mu sigma by root n follows normal 0, 1, right? You might feel that we should just replace this population variance, we should replace it by sample variance, okay? That is intuitively correct, but note that the distribution over here no longer remains the normal. It no longer follows normal distribution, and it gets transformed to another distribution, which is your t distribution. So in order to understand what is t distribution and find out how this basically, so what we will be obtaining finally is that when we replace sigma by s, that is the sample standard deviation, it will no longer follow the standard normal distribution, rather it would follow a t distribution with degrees of freedom n minus 1. It means that we need to first understand what is a t distribution. So then based upon it, we will show how you can obtain this when sigma square is unknown. So whenever you are dealing with any question, you have to make sure whether the variance is known to you or it is unknown, okay? And based upon the situation, the distribution would change. So let us first see what is a t distribution, and then we will come back to the proof of this. So sampling distribution of sample mean when sigma square is unknown. To understand the t distribution, let us first understand some basic other distributions based upon which you get the t distribution. So if we start from the gamma distribution, we say that an absolutely continuous type random variable x is said to follow gamma distribution with parameters alpha and beta if its density is given in this form. And I believe that all of you are familiar with this density, and its mean, if we find it out, it would come out as alpha beta, and variance is alpha beta square. Now, if you talk about the chi-square distribution, so chi-square distribution generates from this gamma only if we replace this alpha and beta with some other quantities. So if you replace alpha with n by 2 and beta by 2, then this gamma distribution is referred to as your chi-square with n degrees of freedom. Okay, and this is the PDF. So in this PDF, earlier one, if you just replace beta by 2 and alpha by n by 2, so you will immediately get the same thing. Okay, and obviously since expectation is alpha times beta, so here n by 2 into 2 will basically give you n, and variance is twice of n, right, alpha beta square. So you can see over here that for chi-square distribution, mean is nothing but the degrees of freedom. So whatever degrees of freedom you have over here, same thing would appear over here, and 2n. So degrees of freedom are basically the number of values which are free to vary. Okay. So in this case, it is n, and chi-square is positively skewed from 0 to infinity. It will take value between 0 and infinity, unlike your normal distribution, which goes from minus infinity to infinity. Now we have some important result which says that what is the relation between chi-square and standard normal distribution. So if x follows your normal distribution, then we have already seen that x minus mu by sigma, it would follow normal 0, 1. And if we further square it up, that is z square, this would follow a chi-square distribution with 1 degrees of freedom. So this can be proved using the distribution function technique. You can easily prove this. So just keep in mind that if x is following normal mu sigma square, then square of the standard normal variate will follow chi-square distribution with 1 degrees of freedom. 1 degree of freedom is appearing. Why? Because here we are dealing with only a single random variable. That is why it is following chi-square with 1 degrees of freedom. We can generalize this further, and if we draw a random sample from this distribution, right? So you standardize each of them, take the summation, and finally what you get is summation zi square. It will follow chi-square with n degrees of freedom. So it says that if x is following normal mu sigma square, then x minus mu by sigma would follow normal 0, 1, which we denote by z. And if I further take the square of this, that is z square x minus mu by sigma whole square, if I do, then I will get chi-square distribution with 1 degrees of freedom. Okay? However, if you suppose that you have n such random variables such that x1 follows normal with mean mu and sigma square, x2 also follows the same distribution, likewise x3, and so on up till xn, right? Now for each of these you can standardize this. So you will have z1, which is x1 minus mu by sigma. Okay, likewise you will have z2, and you will go on up till zn, which will be xn minus mu by sigma. Again, you can square these up. So so what are the distribution of these zi's? Zi, z1, z2, zn? These are standard normal. Now when I square these up individually, z1 square, z2 square, and so on up till zn square, individually all of these are following chi-square with 1 degrees of freedom. However, if I add up all these random variables over here, if I just if I write summation zi square, where I goes from 1 to n, it will follow chi-square with n degrees of freedom. Okay, because here we are dealing with n random variables, so that is why this n degrees of freedom appear over here. Fine. So this is about your chi-square. Now based upon this information, we can define the student's t distribution, which says that if you have a standard normal variate, that is z follows standard normal distribution, and you have another random variable which follows chi-square with r degrees of freedom, and these two are independent random variables, then if you make this transformation that you divide the standard normal one, that is z, divided by square root of u divided by r, so r is the corresponding degrees of freedom, then what you get is that t follows the t distribution, that is student's t distribution with r degrees of freedom. Okay, so once you apply this transformation, it follows our t distribution. Okay, so that is why we first understood what is chi-square, how is it related to standard normal, and you can get chi-square from gamma distribution. So all these distributions are interrelated, and this is again bell-shaped and symmetric about 0. As the degrees of freedom increase, the t distribution approaches the normal distribution, that is a standard normal distribution. So if you have to generate a sample from t distribution, then basically you need a sample from standard normal variate, then you also need from chi-square distribution with r degrees of freedom, and then you apply this transformation, and you will get your t distribution with r degrees of freedom. Now we come to the main result, which is the sampling distribution of the sample mean when variance is unknown. And as I mentioned earlier also, it no longer follows the normal distribution, and it follows the t distribution with n-1 degrees of freedom. Okay, so let us prove this. So this is your theorem number 5. So basically we want a t distribution. We need to have one z, and we need a chi-square distribution with r degrees of freedom. Okay. We have seen earlier also that if x1, x2, xn, these are the random variables which are the random sample coming from normal distribution, then in that case, if I take x bar sample mean minus mu divided by sigma by root n, this follows your normal 0, 1. Okay, so it means you have one standard normal variate, that is numerator is taken care of. Then you need another one, that is chi u. And for this basically, actually, we will prove this result later on in the next theorem. So as of now, I am just using it over here. I will show you the proof. There it will be said that if you denote by n-1 times s square by sigma square, then this basically follows your chi-square distribution with n-1 degrees of freedom. And then these two random variables z and u are also independent. This is the next result which will be coming. But since we are first talking about the sampling distribution of sample mean, I am using that theorem over here. So this is the result, that if you have u as n-1 times s square divided by sigma squared, it will follow chi-square distribution with n-1 degrees of freedom. Since we are given these two, now we can just simply substitute it, because t is what? T is z by square root of u by r. What is z? Z is x bar minus mu sigma by root n whole divided by square root of n-1 times s square by sigma square whole divided by n-1. So n-1 and n-1 would cancel out, right? Sigma would cancel out, and s square, when you take it outside the square root, it will basically be s. So what you get is x bar minus mu s by root n. This we know that this is going to follow t distribution with the same degrees of freedom which are in the chi-square distribution. Okay, in this case u is chi-square with r degrees of freedom, so that is why it follows t distribution with r degrees of freedom. In our case, since it is following n-1 has n-1 degrees of freedom, so t distribution will also be with n-1 degrees of freedom. Okay, so this is the proof. So we have seen that if your sigma square is known, then the sample statistic would be going to the normal distribution. Otherwise, it would go to the t distribution. Okay, it will follow t distribution with n-1 degrees of freedom.